Welcome to this explainer. Look, if you're a focused learner aiming to lock down maximum marks on your upcoming board exams, you are in exactly the right place today. Today, we're diving straight into Chapter 2, Inverse Trigonometric Functions. We're going to cut through all the noise and give you a foolproof visual framework for mastering these concepts so you can walk in a test day with absolute confidence. Let's get into it.
Here is our roadmap for today. We'll cover 1. The invertibility problem. 2. Restricting the domain. 3. The principal value table. 4. Common exam traps. And finally, 5. Solving board exam problems.
All right, Part 1, the invertibility problem, why natural trig functions fail the test.
To really understand inverse trig functions, we first have to ask a fundamental question. Why can't we just instantly invert a standard sine or cosine function? Well, the answer takes us right back to an ironclad rule you learned in Chapter 1 in Class 11. For any mathematical function to even have an inverse, it absolutely must be 1, 1 and on 2, or in formal terms, a bijective function. If it doesn't pass that specific test, you literally cannot talk about its inverse. It's a complete mathematical roadblock.
And here is exactly where the conflict happens. Standard trigonometric functions, over their natural domains, are not 1, 1 and on 2. Think about it. They repeat themselves endlessly like ocean waves. But our strict rule dictates that invertible functions must be purely 1, 1 and on 2. Because natural trig functions constantly repeat their values, they fail this test completely. They simply do not qualify for inverses in their wild natural state.
Which brings us to Section 2, restricting the domain, the mathematical workaround. Getting your head around this workaround is a massive conceptual key for acing your exam. To fix this invertibility problem, mathematicians use a brilliant hack. They literally cut or restrict the standard sine function's domain. If we restrict it to just the tight interval between negative pi over 2 and positive pi over 2, guess what? It stops repeating. It suddenly becomes 1, 1 and on 2, with a range of -1 to 1. And just like that, we are allowed to define its inverse.
We apply that exact same logic to the cosine function. The natural cosine wave goes on forever, but if we boldly restrict its domain to just the interval from 0 to pi, it becomes perfectly bijective. This specific restricted interval, 0 to pi, becomes what we officially call the principal value branch for the inverse cosine function.
This restriction brilliantly sets us up for a great visual trick you can use on your exams. The textbook points out that the graph of an inverse function can be found from the original restricted graph by simply drawing a mirror image, reflecting it directly across the diagonal line y equals x. You are literally just swapping the x and y axes. It's like flipping a pancake.
Okay, moving on to Section 3, the principal value table, your ultimate exam cheat sheet.
Guys, I cannot stress this enough. This definitive table right out of your textbook holds the keys to almost all your 1-mark questions. Mentally screenshot this right now. You absolutely must memorize the specific domains and ranges, the principal value branches, for all 6 inverse trig functions. Look closely for the patterns. Notice how sine inverse, cosecant inverse, and tangent inverse are all grouped around the negative pi over 2 to pi over 2 range. Meanwhile, cosine inverse, secant inverse, and cotangent inverse all hang out in the 0 to pi range. Getting these specific brackets and parentheses locked in your brain is completely non-negotiable for scoring top marks.
Next up, Section 4, common exam traps. Don't lose easy marks to these tricks.
As your virtual tutor, I'd be doing you a disservice if I didn't warn you about the classic examiner tricks that routinely steal easy points from students. You've done all the hard work understanding the core concepts. Please don't let simple notation trip you up. The absolutely crucial point here is to never, ever confuse inverse notation with a mathematical exponent. Sine inverse of x, written with that little -1, is a label for the inverse function. But sine of x enclosed in parentheses and raised to the power of -1, that's an actual exponent, and it equals 1 over sine x. Conflating these two things is literally the #1 trap examiners set on board exams. So let's summarize these golden rules straight from the textbook into a quick mental checklist you can run through during your test. First, watch out for the notation trap we just talked about. Second, if a question doesn't specifically mention a branch, just always assume they want the principal value branch from that table we just memorized. And finally, remember that your ultimate answer, the principal value, has to be an angle that perfectly fits inside that specific branch's range. If it doesn't fit, it's not the principal value.
Finally, Section 5, solving board exam problems, a repeatable framework for 1-mark and 2-mark questions.
We are on the home stretch now. Let's shift gears into direct application to guarantee you get full credit. We'll look at example 1 from the book, find the principal value of sine inverse of 1/2. Here's a highly repeatable 3-step algorithm you can use every single time. Step 1. Set up your equation. Let y equal sine inverse of 1/2, which means sine of y equals 1/2. Step 2. Write down the principal value branch. Explicitly state for the examiner that the range for sine inverse is -π/2 to π/2. Show them you know the rules. Step 3. Simply identify the angle within that specific range that gives you a sine of 1/2.
Now wait a second. Actually, scratch that. Let's think about our trig tables for a moment. Sine of π/6 is 1/2, right? Right. So our principal value is actually π/6, and π/6 fits perfectly within our restricted domain range. If you write this out step by step just like this on the exam, your mark is mathematically guaranteed.
Let's quickly run through example 2 to see how this exact same framework handles negative values seamlessly. We want the principal value of cotangent inverse of -1/√3. Step 1, let y equal the function, so cotangent y equals -1/√3. Step 2, deal with that pesky negative. We know cotangent of π/3 is +1/√3. By tapping into our trig identities, cotangent of π minus π/3 gives us the negative value we need. Step 3, simplify that down to cotangent of 2π/3. Because 2π/3 sits perfectly inside a required open interval of 0 to π for cotangent inverse, boom, that's our final answer, y equals 2π/3.
And that brings us to the end of our framework. To wrap up this explainer, I want to leave you with an actual question straight out of exercise 2.1 in your textbook. Find the principal value of tangent inverse of -√3. Think about the 3 steps we just covered. What is your principal value branch here? How are you going to handle that negative sign? I highly encourage you to grab a piece of paper and apply your new framework to this problem right now. Thank you so much for joining me on this explainer. Keep that principal value table locked in your mind, and best of luck destroying those board exams.